Hi everybody, Professor Burns here. We're going to take a look at section 4.6, which is our final new lesson for Unit 2, where we're looking at another method for solving second-order differential equations called variation of parameters. So make sure that your cell phones are put away, you have your notes packet out, and you're ready to listen carefully for the next 15 minutes or so. So in the last sections, we looked at the method of undetermined coefficients, and that allowed us to find solutions for certain types of equations where we had a constant coefficient in the equation. This time, we're going to look at what to do when we have another function as the coefficient for the equation. So let's talk about the method first, and then we'll go through an example of it. So we're looking for a particular solution to the differential equation in the same format as what we're used to. But the difference now is this function on the right side may not fit one of the special formats we talked about in the previous section. So here's the way we're going to handle this. We're going to find first a fundamental solution set. In other words, two particular solutions that would work for the corresponding homogeneous equation. As usual, set it equal to 0 and solve. And so y1 and y2 are going to be two particular solutions that would work. And we're going to call the particular solution then to our general differential equation, v1 times y1 plus v2 times y2, using the superposition principle. And then the next step would be to figure out what v1 and v2 are. And the way we're going to do that is we're going to solve a little system of equations that I have down here for v1 prime and v2 prime, and we're going to integrate those. And then we're going to substitute that back in, and that'll get us a particular solution to the original differential equation. So let's do an example here. We want to find the general solution to the differential equation that's given here. So let's start by looking at the homogeneous equation that goes with this equation, this differential equation. So we have y double prime plus 9y prime equals 0. And the characteristic equation, of course, is r squared plus 9 equals 0, r squared equals negative 9, so r equals plus minus 3i. So let's start with the complementary solution, y sub c, and this using the same formats we've been using in the previous sections, since these are complex solutions where alpha would be 0 and beta would be 3. We end up with c1 times cosine of 3t plus c2 times sine of 3t. And we're going to come back to this later. But now, to get going on the particular solution that we're going to put together to get our general solution, I need to find this fundamental solution set. So what I'm going to do is I'm going to choose values for c1 and c2 that give me two particular solutions. So suppose, for example, that c1 is equal to 1, and let's say c2 is equal to 0. Let's keep it simple here. So if that's the case, my particular solution y1 becomes c1 is 1, so cosine of 3t, and then if c2 is 0, this sine term goes away. Now let's also suppose that we had a solution where c1 is 0 and c2 is 1. Then another solution that would work would be where c1, if that were 0, the first term goes away, c2 is 1, that gives me sine of 3t. So this is called my solution set that I'm going to use, a fundamental solution set for the homogeneous equation. And I'm going to write that using this notation, cosine of 3t, comma, sine of 3t, so just set notation. All right, so then the next step is to go ahead and just write this. Let's write y sub p using this notation here, v1 y1 plus v2 y2. So let me write that down here. So we're going to have y sub p of t is going to be equal to v1 times y sub 1 of t plus v2 times y sub 2 of t, and let's fill those in. So y sub p is equal to v1, which we don't know, I'm just going to call it v1. y1 is the cosine of 3t plus v2 times y2, which is the sine of 3t. Now, the second step, or the next step, I should say, is to solve this system of equations. And this can get a little bit complicated algebraically, but let me go ahead and show you how to set it up, and then let's kind of see what we wind up with. So we've got y1 times v1 prime plus y2 times v2 prime equals 0. So y1 is the cosine, so cosine of 3t times v1 prime plus y2, which is the sine of 3t times v2 prime, needs to equal 0. So this is multiplication, just keep that straight. And then the second equation would be y1 prime times v1 prime plus y2 prime times v2 prime. So let's figure that out. So y1 prime requires a chain rule, so that would be negative 3 sine of 3t times v1 prime plus, same thing here, chain rule here, so 3 cosine of 3t times v2 prime, and now that should equal f over a. So f is the function that was on the right side, a of course is that leading coefficient, so for us f is this tangent function, 3 tangent of 3t, and then of course a is just 1 in my example here. So this is my system of equations that I need to solve. So we're going to do a little bit of algebra here, and what I'm looking at my notes now, what I think I did is I went ahead and I used substitution. I took the first equation and I solved it for v1 prime. So take that first equation and rewrite it so that v1 prime is by itself. Go ahead and pause the video and make sure you get the same thing I do, but I'm ending up with v1 prime is equal to negative sine of 3t over cosine of 3t times v2 prime, and that of course is just tangent, so negative tangent of 3t times v2 prime, and then I substituted that into the second equation in place of v1 prime. So I have negative 3 sine of 3t times negative tangent of 3t times v2 prime plus 3 cosine of 3t times v2 prime equals 3 tangent of 3t. And this is a horrible looking equation, but the point is it's only got one variable, and that's the v2 prime that I need to solve for. So let's do a little bit of algebra here. Sine times tangent, tangent is sine over cosine, so that first term becomes a positive 3 sine squared of 3t over cosine of 3t times v2 prime plus 3 cosine of 3t times v2 prime equals 3 tangent of 3t. And then if we get a common denominator between these two, the common denominator will be cosine, so I wind up with 3 times the sine squared of 3t times v2 prime plus 3 times cosine squared of 3t times v2 prime, right? I'm getting a common denominator, multiply this term by cosine of 3t on the top and bottom, all over cosine of 3t equals 3 tangent of 3t, and hopefully that trig identity is popping out at you. You've got sine squared plus cosine squared, so that gives me 3 times sine squared plus cosine squared, which is just 1. So I end up with 3 times 1 times v2 prime over cosine of 3t equals 3 tangent, and tangent of course is sine of 3t over cosine of 3t. So just do sort of a little one-to-one correspondence here. They both have cosine 3t as the denominator. They both have 3 in the numerator, so that means v2 prime has to equal sine of 3t right here. This v2 prime has to equal sine of 3t. And then v1 prime, remember that v1 prime we said earlier was equal to negative tangent of 3t times v2 prime. So let's fill that in here. So v1 prime, actually let me make a little bit of space. So here we go. We said v1 prime was equal to negative tangent of 3t times v2 prime, which we just said was sine of 3t. And I'm going to leave that in that format for now. I don't think anything would cancel out. You'd have sine squared over cosine. Let's just leave it like that. So let me highlight a couple of things here. So this is my V2 prime term. This is my V1 prime term. And don't forget back here we had our Y1 term and our Y2 term. So if we integrate to get V1, that's going to be the integral of negative tangent 3t times the sine of 3t. And I'm gonna skip the details here, but if we did some trigonometry and made some replacements with some trig identities, take my word for it for now. We can go over this a little more detailed in class, but what we end up with is negative 1/3 times the natural log of secant 3t plus tangent of 3t plus 1/3 times the sine of 3t. And as I said, we can go over the details in class, but this is not terribly difficult integration once you use some trig identities. And then V2 is going to be the integral of sine of 3t, which is pretty straightforward. That's just going to be negative 1/3 cosine of 3t. All right, so here we go. Let's put it all together. So y sub p, my particular solution then, is going to be, we're going to put everything together. It's going to be V1, which is negative 1/3 natural log. Actually, let me just write this. Natural log secant of 3t plus tangent of 3t plus 1/3 sine of 3t. And all of that gets multiplied by y1, which, as we recall, y1 was cosine of 3t. So I'm just going to stick that in here at the end. And then plus V2, which is negative 1/3 cosine of 3t times y sub 2, which is sine of 3t. So we have negative 1/3 cosine 3t of sine of 3t. And then, so this is the particular solution if we were asked to find that. The question did say actually to find the general solution, so remember how to do that. The general solution, of course, is y sub c plus y sub p. So I'm going to put all this together. I think that ends up giving us, let's see, we've got c1 cosine of 3t plus c2 sine of 3t. And then observe back here that because you had a positive 1/3 sine of 3t cosine of 3t, and then you had a negative 1/3 of that same term, those actually ended up canceling out and just leaving me with that natural log term. So minus 1/3 times the natural log of secant 3t plus tangent of 3t. And that's it. That's going to be our general solution to the original differential equation. So you can see this method gets pretty into the weeds, especially solving that system of equations that we had back here. We'll actually use technology in class to work those. We can use Wolfram Alpha to solve those systems, or we'll make sure it's a really simple equation either way. So we'll simplify this a little bit in class, but I just wanted to show you that this is another method we can use when the right side of that second order equation doesn't fit one of the formats we talked about in the previous section. So make sure you bring your notes with you to class, and I'll see you then.